Hello, welcome to this presentation on my latest paper titled Explainability of Large Language Models Using SMILE, Statistical Model Agnostic Interpretability with Local Explanations. I'll begin with an introduction to large language models and the importance of interpretability, followed by a review of related work that informed our approach. Next, I'll walk you through the problem formulation and our proposed method, SMILE, which stands for Surrogate Modeling for Interpretable Local Explanations. After that, we'll discuss how we evaluate SMILE using a range of interpretability metrics, and I'll share experimental results and insights from applying it to models like GPT, Claude, and LLama. Finally, we'll wrap up with a conclusion, outline some future directions, and briefly cover the references that support this work. Large language models, LLMs, leverage deep neural networks to process and generate text based on natural language commands. They excel in transforming intricate instructions into coherent, contextually relevant outputs, enhancing user interaction and understanding. This capability is pivotal in advancing the explainability and functionality of AI systems. One of the biggest issues with large language models is that they work like black boxes. First, there's a lack of transparency. It's hard to know how the model makes decisions or why it gives a certain answer. Second, they're difficult to debug. When something goes wrong or a response seems off, we can't easily trace the problem. Third, there's inefficiency in prompt design. Users often have to go through a lot of trial and error just to get the output they want. And finally, performance can be unpredictable. You might give two very similar prompts and get very different results, which is frustrating and unreliable. These challenges highlight the need for interpretability, which is what this presentation focuses on solving. To address the challenges, we introduce our method called SMILE. SMILE helps improve model transparency by using ECDF, empirical cumulative distribution functions, to explain how model decisions are made. It also supports debugging by showing which parts of the prompt are affecting the output, so we can identify problems more easily. For command optimization, SMILE helps users reduce the trial and error process by highlighting what wording actually matters. And finally, SMILE improves consistency by minimizing unexpected changes in model behavior across similar prompts. Large language models, LLMs, are advanced neural networks trained on vast text datasets to mimic human language. Notable models include GPT-4, PaLM, Claude, and LLama. They excel in few-shot and zero-shot learning, allowing task generalization with minimal training. Techniques like reinforcement learning from human feedback, RLHF, enhance alignment with human values, ensuring safer interactions. But why LIME? One popular method is LIME, which stands for Local Interpretable Model Agnostic Explanations. LIME is great because it's model agnostic, meaning it works with any AI system, and it doesn't require access to internal of the model. It creates simple local explanations that are easy to understand. Over time, several methods have been built on top of LIME. SMILE uses statistical distance metrics like Wasserstein distance. US LIME focuses on selecting examples close to the model's decision boundary, and BayLIME brings in Bayesian models. Recent advances in LLM explainability include the SIA framework, which enhances interpretability through self-explainability mechanisms. The CEL framework integrates concept-based explanations into training, advancing mechanistic interpretability. Anthropic research shows how mechanistic interpretability aids in understanding model behavior. ConceptX uses a coalition-based Shapley framework to highlight semantically meaningful input phrases, providing robust human-aligned explanations. Let's define the problem we're solving. We start with an input prompt, like a sentence or instruction. Then we create small variations of this prompt, which we call perturbations. We look at how a language model responds to the original prompt and to each of the perturbed versions. This gives us a distribution over the model's outputs. We measure two things: input distance, how different the perturbed prompt is from the original, using word movers distance; output shift, how much the model's responses change, measured using the Wasserstein distance between output distributions. Now we want to explain the model's behavior using something simple and interpretable. To do that, we fit a local linear surrogate model, but we don't treat all perturbations equally. Those closer to the original prompt are more important. So we assign them weights using a Gaussian kernel. Prompts that are very similar get higher weights. Each perturbed input is turned into a feature vector, and we use linear regression to fit a model that predicts how much the output changes. The idea is to use this surrogate to explain which parts of the input have the most influence on the output. Why is it okay to use a linear model here? Because of a concept called Lipschitz continuity. If our original model is Lipschitz, meaning its output changes smoothly as the input changes, then the output shift function we just defined is also Lipschitz. That means we can safely approximate it with a linear model, at least locally. So this gives us both a practical method and a solid mathematical reason to trust the local explanations we generate with SMILE. Our solution, SMILE. In image classification, SMILE works by dividing an image into smaller regions called superpixels. These regions are randomly kept or removed to create perturbed versions of the image. By observing how the model's predictions change and measuring the difference using a statistical distance like the Wasserstein distance, SMILE identifies which regions most influence the model's decision. In our work, we extend this idea to text. We input a prompt into the language model, break it down into individual words, and generate perturbations by including or excluding certain words. The model then produces responses for both the original and perturbed prompts. We compute the Wasserstein distance between the outputs to assess how much each perturbation affects the result. These distances serve as similarity scores. We then calculate weights based on input differences and fit a weighted linear regression model. The resulting coefficients tell us how important each word is. Finally, we visualize the attributions as a heat map. To evaluate SMILE, we use 4 key metrics. 1. Accuracy. This checks if the words SMILE highlights match the true important words. We use a score called attribution AUC for that. 2. Faithfulness. We test how much close our local explanation to the behavior of the original model. 3. Consistency. We check the model gives similar explanations in various time for the same prompt. 4. Stability. Finally, we look at whether small changes to the prompt cause big changes in attribution. A stable system shouldn't. These metrics help ensure our explanations are accurate, trustworthy, and reliable. This slide shows the different metrics we use to evaluate fidelity, or how well the surrogate model approximates the original model's behavior. We include several key metrics. Weighted R-squared, R2W, measures how closely the predictions match. WMSE and WMAE are weighted error metrics, incorporating the importance of each data point. And finally, mean L1 and mean L2 give us average error in absolute and squared terms. The framework assesses prompt-level interpretability in large language models using 6 sentences. This approach identifies the most influential words in a prompt. By analyzing these sentences, we can better evaluate the transparency and reliability of language models across various applications. Here we compare our explainability method SMILE with a well-known example from Anthropic's research. At the top, you can see Anthropic's reasoning path, which breaks down how the model processes each part of the input to arrive at an answer. Below that, we show how SMILE provides a different but complementary view by assigning importance scores to each token in the prompt. For example, in the sentence, "The capital of the state containing Dallas is," SMILE highlights Dallas as the most influential words. The MMLU-based dataset evaluation of SMILE on ChatGPT reveals insights into its performance across diverse tasks. SMILE demonstrates robust capabilities in understanding and generating language, highlighting its potential in enhancing explainability. This evaluation underscores the importance of comprehensive testing to ensure reliable AI model performance. Here, we applied SMILE to 2 optimized prompts from Google's OPRO framework designed for zero-shot mathematical tasks. Using GPT 3.5 and GPT 4, Smile highlights the most influential words in each instruction. In GPT 3.5, key terms like arithmetic and solution stood out. In GPT 4, numerical, command, and answer were most impactful. This shows how Smile helps uncover which words truly drive model behavior in optimized instructions. In evaluating model accuracy, we consider attribution accuracy, F1 score, and OROC. OpenAI GPT scores 0.70, 0.59, and 0.84 respectively. LLama achieves 0.76, 0.40, and 0.84, while Claude AI leads with 0.82, 0.67, and 0.88. These metrics highlight variations in model performance based on input prompt changes. For stability analysis, we use the Jaccard index, reveals consistency in token attribution across perturbations. OpenAI GPT scored 0.62, indicating higher stability compared to LLama and Claude AI, which scored 0.45 and 0.44 respectively. This metric highlights the robustness of OpenAI GPT in maintaining consistent attributions, crucial for reliable model interpretability. To measure consistency, we ran each model 10 times on the same prompt. We used variance and standard deviation as metrics. As you can see in the table, OpenAI GPT showed the most consistent behavior with nearly zero variance. In contrast, LLama and Claude AI had higher variability in their outputs. Here, we evaluate fidelity using the prompt, "What is the meaning of life?" Each model was tested on 32 perturbed versions of the prompt. We measured how well our surrogate model fits the model's behavior using metrics like WMSE, WMAE, and weighted R2. As shown in the table, OpenAI GPT had the highest weighted R2 score, meaning it was the most faithful to the original model behavior. This slide shows how fidelity changes as we increase the number of prompt perturbations from 32 to 256 for OpenAI GPT. As we add more perturbations, we see a drop in WMSE and WMAE, meaning the surrogate model fits better. Interestingly, the weighted R2 score doesn't always increase. Here we apply the same evaluation as with GPT, testing LLama across 32 to 256 perturbations. As the number of perturbations increases, we see a consistent decrease in error metrics like WMSE and WMAE, which indicates better surrogate model performance. However, similar to GPT, the weighted R2 scores drop as perturbations increase. For Claude AI, we use the same setup from 32 to 256 perturbations. Interestingly, Claude performs very well at 32 perturbations, with the highest weighted R2 score of all models at that level. However, as we increase perturbations, fidelity drops, especially in weighted R2 values. While error metrics like WMSE and WMAE improve at 64 and 128, they don't hold at 256. Here, we compare how different distance measures, Wasserstein and Cosin, affect fidelity across two surrogate models, LIME, SMILE, and BayLime. The best performance is achieved using Wasserstein distance for both text and output, with the highest weighted R2 of 0.7104. These results show that Wasserstein distance consistently provides better fidelity, especially for text perturbation analysis. This slide compares the execution times of LIME, SMILE, and BayLime across three language models using 60 perturbations. As shown, SMILE takes slightly more time, especially for Claude AI, indicating higher computational complexity. However, this added cost comes with clear benefits. SMILE provides better fidelity and shows greater robustness to adversarial attacks. So while SMILE is more complex, it delivers stronger and more reliable explanations, a worthwhile trade-off for critical applications. In this analysis, we use 10 prompts that all convey the meaning of life, but with different sentence structures. The box plot shows attention scores for the tokens meaning and life across these variations. As you can see, attention to each word changes based on how the sentence is phrased. This demonstrates that even subtle changes in syntax can shift the model's internal focus, which has key implications for prompt design and interpretability. To wrap up, interpretability is crucial for applying LLMs in sensitive areas like healthcare, business, and education. Without it, trust and adoption drop, and with new AI regulations pushing for transparency, black box models face real risks. Our method, SMILE, addresses this need. It helps explain outputs by showing which words in the prompt influence the model's response. It's model agnostic and works with GPT, Claude, Llama, and Gemma, offering stable and practical insights for users and developers alike. Looking ahead, there are several ways to extend this work. First, we plan to apply SMILE to mathematical text generation using models like Minerva or MathLLM for symbolic reasoning tasks. We'll also explore paraphrase models to understand how style and tone shift with prompt changes. Next is adapting SMILE for multi-turn dialogue so it can track attribution over multiple conversational steps. We aim to generalize this method across more tasks like summarization and classification, what we call cross-task generalization. Finally, we're working on interpretability benchmarks to standardize how we measure fidelity, stability, and attribution robustness. In here, you can see the references and the rest of the references. Thank you for watching this presentation. For more details, please refer to the full paper available in the description below.